Hello there. I'm going to be showing you in the section 11.3 video a couple of new convergence tests for series called the integral test and the p-series test. So I'll be showing you how to determine if a series converges using those two tests, and also kind of keeping in mind that we have learned the divergence test as well as the geometric test. Okay, so let's start off by just defining some terms and explaining what these vocabulary words are. So for the integral test, suppose that we have a sequence of numbers. All the numbers are positive and the numbers are decreasing. So we have a sequence of numbers that are decreasing, but they're all positive. Then the series of that sequence, of the numbers, to add all those numbers together, the series will converge or diverge the exact same way as the integral converges or diverges. So the integral test basically matches up the convergence divergence of a series with the convergence divergence of an integral. So we can start doing integration to determine whether a series converges or diverges, with the expressed caveat that all of the numbers are positive and they're decreasing. By the way, decreasing is not a big deal, because if the numbers weren't decreasing, then by the divergence test, we know that the limit wouldn't be zero, and therefore it would diverge. So we're pretty much going to be able to easily show that these are decreasing and that all the terms are positive. So as long as we can find the integral, we can determine whether the series converges or diverges. For the p-series test, it's another one of these very specific looking series. So for the p-series test, we need a series that looks like 1 over a number to a power. And the p is a number itself as well. So n, I should have said the number 1 over n to the p, where n is the variable. It's the thing that's moving. We're doing n equals 1 to infinity or something like that, of 1 over n to the p. So this is like a polynomial, like n squared or x squared. Although for whatever reason they write it in the denominator. So normally we're seeing polynomials as, x to the fifth, x squared, x whatever on the numerator. Here we're doing those same things, but in the denominator. So 1 over n to the fifth, or 1 over n squared. And they don't have to be whole numbers. They can be fractions or anything like that. And we know that if you can write the series in the specific form of 1 over n to a constant, then it will converge as long as that constant, that exponent, is greater than 1, and it will diverge whenever the constant is less than or equal to 1. When it's equal to 1, by the way, that's that harmonic series. That's a very specific thing. If we can write it in that particular way, we can say by the p-series test whether it converges or diverges. All right, let's see some examples. I have the harmonic series right here, 1 over n. You may remember that from a previous video. If you write out the terms of 1 over n starting with 2, you get 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. That is the harmonic series. We do know that the harmonic series diverges. We've seen it a couple times before, but we're going to use the integral test this time to see if it, in fact, does diverge by this test. So we have to see if these are positive. 1 over n is greater than 0, for n greater than 2. And that's certainly true. And 1 over n, it gets smaller as the denominator gets bigger. It's smaller, so they get smaller terms get smaller. So we've done our due diligence, checking that the terms are positive and that the terms do get smaller. Okay, we can also do the limit as n goes to infinity and show that it's equal to 0, so that's getting smaller to 0. So what does the integral test says? We're supposed to use the integral test. So instead of doing the sum, we do the integral of 1 over n. We need some numbers here. So dn, n equals 2 to n equals infinity. And this, my friends, is an improper integral. We've done improper integrals before. So all we do is we just do a little limit thingy thing. And we replace infinity by this variable, like say b or whatever. So we do 2 to b instead of 2 to infinity. And then we do our normal antiderivative stuff, and then we do the limit as b goes to infinity. So we're doing the limit from 2 to b. B is tending to infinity. And we're doing it of the same exact function, 1 over n. The antiderivative of 1 over n is ln of n. And I need to make some more space. Sorry. We have the limit as b goes to infinity of ln of n, but we need to evaluate that between 2 and b. All right, so we just got to plug in the numbers and subtract. So we get the limit as b tends to infinity of plug in the b, plug in the 2, subtract, and then of course we have to take the limit as b goes to infinity. So what happens to ln of b as b tends to infinity? We get to like ln infinity. What is ln of infinitely? Something infinitely large. You may remember me drawing this picture and suggesting that you have a basic library of the most common dozen functions in mathematics, natural log being one of them. Natural log looks like this. It heads off to infinity kind of slowly. So ln of infinity goes to infinity. Infinity minus a number is still infinity. So this is equal to infinity. In other words, this integral diverges. It doesn't equal a number. So since the integral diverges, so this thing diverges. And then I can say thus, according to the integral test, we have the series of 1 over n also diverges, because the series diverges or converges in the same way that the integral diverges or converges, as long as we have those basic ideas that the numbers are positive and getting smaller. Diverges by, and we will say, the integral test. And there we go. So there's the first problem to show that this series right here diverges using the integral test. It is a harmonic series, so generally you could say, hey, that's a harmonic series. We know the harmonic series diverges, but for this particular example, I wanted to show you that the integral test can demonstrate that this series does in fact diverge. In fact, the next problem, we're going to do the same problem, but we're going to be using the integral test. Excuse me, the p-series test. I got to read my own wording here. So we're going to do the same darn problem. We know the answer is still, it's going to diverge, but we're going to be using another test just to see how it works using the p-series test. So what is the p-series test? The p-series test says you have to write it as 1 over n to the p. So this would be the series from 2 to infinity of 1 over n to the 1. Right? So this is a p-series test. It does fit the 1 over n to the p format, 1 over n to the p, where in this case, p is equal to 1. So it's 1 over n to the first power, p is equal to 1. According to our formula here, according to our p-series test, it will diverge for any p less than or equal to 1. So this is definitely less than or equal to 1. So this original series that we have, the harmonic series thing, will diverge by the p-series test. And I'll even put in here p is equal to 1, just to up my game in terms of my justification. All right, so that's just as simple as that. P-series test also shows that the harmonic series diverges. All right, let's get away from the harmonic series and let's do some other problems. So I got maybe 7 or 8 more to do for you here. They're all kind of quick. So let's show you the next one. For this one right here, I have a series of 1 over square root of n. We're going to rewrite this using algebra, using fractional exponents, because our math just works so much better with numbers than with weird symbols. So this is n to the 1/2. Same thing as square root. And you may recognize this as a p-series. This is a p-series. How do I know it's a p-series? A p-series has the variable as the base and it has a number as the exponent. It's the reverse of the geometric series. We did geometric series in the previous section. That was where we had a number as the base and an exponent. So we had a number raised to a constant, used to a variable. So this was a number raised to the variable. This is geometric or exponential. For example, you have like 3 to the n, a number raised to a variable. That's the geometric number to a variable. If you had a variable raised to a number, that's the reverse. A variable raised to a number, that would be like n to the 3, right? So you have a variable raised to the number versus a number raised to a variable. This is called a p-series, or what I oftentimes call a polynomial p-series. As long as you have the idea that polynomials or p-series don't have to have whole numbers, which oftentimes people think about when they think of polynomials. Nonetheless, this is a p-series with p is equal to a half. It fits that 1 over n to the p format, where the constant exponent number is a half. So according to our p-series test, if you have something that looks like this, 1 over n to the p, it will converge for any p larger than 1, and it will diverge for any p less than or equal to 1. What do we have? We have 1/2. So that's less than 1. So we know that this series will diverge by the p-series test. And I'll just put p equals a half in parentheses, emphasizing that it's certainly less than 1. Or maybe I'll say p, I'll be like super like judgmental or not, super justifying. P is equal to 1/2, which is less than 1. Okay. And so we know that this thing diverges. It doesn't really matter if I start with 1 or 2, but in this case, it does start with 1. So we know that this thing diverges by the p-series test. All right. Next one on this page, last one on this page, 1 over 2 to the n. 1 over 2 to the n. So this is not a p-series because p-series is a variable to a number, and this is a number to a variable. So this is essentially a geometric series. So this is really geometric. I got to be able to spell geometric. And we can write this as 1 over 2 to the n, and that would fit our geometric series format. And because the value of r is between -1 and 1, r is a half, right? Our number, our base being raised is a half. We know this converges by the geometric test. But what I want to do is I want to show you that this also converges using the integral test. So I want to just practice the integral test and the p-series test a couple of times. So we do know this converges by geometric test. And if you had this in the homework or on a test or something, you could just say, hey, I know by the geometric test this converges and be done with it. If the instruction said specifically to use the integral test, this is how you would do it. So you want to see that these are positive. So 1 over 2 to the n are all greater than 0 for n greater than or equal to 0. The reason I have n greater than 0 is because it starts at 0. So when n is 0, it's 2 to the 0, which is 1, and they're all positive. They're all positive numbers. And then 1 over 2 to the n is going to be larger than 1 over 2 to the n plus 1. And you could just do a basic argument. The denominator is larger. Remember, we have this argument when the denominator is larger, then the value of the fraction, the value, I got to spell value correctly, value of the fraction or the whole thing is smaller, right? Larger denominator means a thing gets smaller, so it's getting smaller. 1 over 2 to the n, 1 over 2 to the n plus 1, 1 over 2 to the n is going to be smaller because the denominator is larger. So we have to demonstrate that the terms are positive and decreasing for us to be able to use the integral test. So integral test we can use now. We confirmed the two basic ideas of the integral test, integral test. What we do is instead of doing the sum, we do the integral from n equals 0 to infinity of 1 over 2 to the n dn. And if this integral converges, then our series converges. If this integral diverges, then our series diverges. And just a reminder, we'll go ahead and do the steps. The way you do an integral like this, it's called an improper integral. What you do is you just do a limit. You make up some letter like b, and you just go from 0 to b instead of 0 to infinity. 1 over, or I'm going to write this as 2 to the negative n dn, just to make it easier to anti-differentiate when it's just like one base of 2 instead of a fraction. We might use some u substitution here. U is equal to negative n. Du dn is negative 1. So our dn becomes negative du. And we can integrate this. A lot of people know how to integrate this without doing a u substitution. But I'll let you fill in the details for the u substitution as you wish. And when you integrate this, what you get is you get, well, I'll write it out one more step. So limit as b goes to infinity of these are n values. I haven't changed them over to u values because I'm going to change it back. So n equals 0 to n equals infinity. 2 to the negative n in the u world becomes 2 to the u du with a negative out there in front, which we don't care about. We can even put in front of the integral sign if we wish. And the integral of 2 to the u du, it's one of our standard formulas for antidifferentiation. The integral of 2 to the u du is 2 to the u over ln2. We do need the negative. We do need to go from n equals 0 to n equals infinity. But we're going to put these this u thing back in terms of n before we plug stuff in. So we get the limit as n goes to infinity of negative 2 to the, what's u? U is negative n, to the negative n over ln2. And then we just go from 0 to infinity. Plug in the numbers and subtract. So, oops, I wrote 0 to infinity, but of course it's supposed to be 0 to b. And I'm spacing on the whole fact of why we put a b in there in the first place. Because you can't put infinity on an integral sign because integrals have to be from numbers. So I got to go correct myself again, as I oftentimes do in these videos. But as you know, and if you've heard me before, I don't like just editing these to pretend like I do everything 100% correct the first time, because that's just not reality. All the people doing math out there make little mistakes and then either hide them, or like me, I just say, hey, that's the way life is, right? So we're going from 0 to b, and limit as b goes to infinity. Yeah, so I messed up all the stuff here. So I guess I'm getting ahead of myself. Like sometimes your brain like goes faster than your hand. So I'm thinking like I got to put an N in there, I got to put a B in there. So let me just review to make sure there's nothing else I need to correct. All right, so I'm doing this antiderivative of 1 over 2 to the n, which is really 2 to the negative n. It goes from 0 to infinity, which I can't do. So I go from 0 to b and let b as a limit tend to infinity. So now I can just go 0 to a number and then make the number tend to infinity. To integrate, to anti-differentiate 2 to the negative n, I do some sort of u substitution kind of thing. And that ends up being negative 2 to the u du, which I do know the antiderivative of 2 to the u du. My integral is still going from n equals 0 to n equals b, right? Still those values from 0 to b instead of 0 to infinity. If I anti-differentiate 2 to the u, I get 2 to the u over ln2. The negative is still there, and now I have to plug in the values 0 to b. But remember, those are n values, n equals 0 to n equals b. I can't plug n values in for u, so I'll just put u back. Since u is negative n, I put it back as negative n. So I'm still taking the limit. I'm going from 0 to b, and I'm just going to plug in the numbers. So I get negative, when I plug in b, I get 2 to the negative b over ln2. And when I plug in 0, I get 2 to the 0 over ln2. I guess a minus I can write as a plus. But let's see what happens here. The limit as b goes to infinity of negative 2 to the negative b over ln2. This is the same thing as 1 over 2 to the b ln2, which is 1 over infinity, which all tends to 0. 1 over something infinitely big is equal to 0. A minus is a plus. 2 to the 0 is 1 over ln2. 1 over ln2 doesn't have anything to do with b. So that is a finite or a converging integral. So this is equal to 1 over ln2. So it converges. So if the integral converges, then we know that the series converges. So the series of what was our series again? 1 over 2 to the n, right? 1 over 2 to the n. Our series of 1 over 2 to the n converges by the integral test. And I think this was 0 to infinity. Again, it doesn't really matter too much. We're just looking for whether the sum is finite or not. And the sum is finite because of the integral test. It also is true because of the geometric series test. All right, let's do maybe 4 more examples just to help you see the idea of the integral test and the p-series test. Okay, so n equals 2 to n equals infinity, that series of numbers of ln n over n. So let's see what happens with ln over n. Ln over n, ln over n, these are all positive values. For n bigger than 2. The ln of 2 is a number that's bigger than 1. I'll show you the ln graph again if you'd like to know, and I'll put a number in there so you can get a size of the scale. So the ln graph, as I've written out a couple times before, goes like this. Goes off to infinity. And this point right here, which is an x-intercept, is at 1. So that's where x equals 1. Let me write down ln equals ln x. This is the ln x graph. At 1, the y value is 0. At 2, the ln value is bigger than 0, right? So ln 2 is bigger than 0, divided by 2 is still bigger than 0. So they're all bigger than 0. All right, are the numbers getting smaller? Yes, they're getting smaller because the derivative is less than 0, right? It's a decreasing, or no, it's increasing at a decreasing rate. So the derivative is here, but the derivative is getting smaller. So the second derivative is less than 0. But you can also just see this on the picture. The values are getting smaller and smaller. We can also just do derivatives and show that the derivative is getting smaller and smaller. And so therefore it is decreasing. So it has to be positive, and we have to show that ln of n over n is bigger than ln of n plus 1 over n plus 1. And we can do that just by looking at how the derivative behaves. So we can take a derivative of this thing and then show that the derivative is getting smaller, right? Right. So let's write out our function. Y equals ln of n over n. Its derivative, well, this is a quotient rule. So derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So that's just going to be, and 1 over n times n is 1 minus ln n over n squared. So that's the derivative. And you can take the second derivative to show that it's a negative, but you can also just show that the derivative is getting smaller by saying it's 1 minus ln n. So as n gets bigger, this becomes a smaller and smaller number. And so this is going to be a decreasing. So this is gets smaller as n gets bigger. Right? You could stick it in like 2, n equals 3, n equals 4. You get 1 minus a bigger and bigger number, which is, a smaller and smaller number. Okay, so we can show that it is getting smaller and smaller. You can also take the limit as n goes to infinity of ln of n over n, and use L'Hopital's rule. We did this before. We can show that it's infinity over infinity, and we can use L'Hopital's rule to simplify the limit to 1 over n over 1, which tends to 0. So we have positive numbers that are all distinct. They're getting smaller to 0, so we know that the integral test applies. I'm just trying to do this in various ways to show you that you can't just say integral test and just wave your hands. You have to give some justification of why the integral test applies or can be used. It can be used if the numbers are all positive and they're getting smaller. All right, so we can use the integral test, right? So we can use, so let me put that in green or something. So we use the integral test. So the integral test says we can do the integral instead of the summation, and then we can determine based on the integral whether the original sum of the series converges or not. So we'll do an integral of this function, ln n over n. We will go from 2 to b, where b is tending towards infinity. This is another u substitution problem where we let u is equal to ln of n, and then du dn is equal to 1 over n. Oops, I forgot the dn over here. So if you solve for dn, then you get n du. And you can simplify this limit as ln n was u, and dn was n du. This is n. Let me write that clearer. dn is n du. So this becomes n du. The n's divide out, and you end up with the limit as b goes to infinity. These are still n values, by the way. N equals 2 to n equals b. And here the n's divide out. We get u du, which we know the antiderivative of u du. Integral of u is u squared over 2, or 1/2 times u squared. We do have to evaluate these from 2 to b. I'm going to put the u back in terms of n's before I plug in the stuff. So this becomes, what was u? U was ln n, so it becomes ln n squared over 2. And now I can plug in 2 and b and take the limit. So this is how the integral test works. You convert it into an integral, and then you do the improper integral thing and do your limit. Takes a few steps, but it is pretty straightforward. Let's plug in the b. Let's plug in the 2. I get ln of b squared over 2 minus ln of 2 squared over 2. Right, so I got to plug in the b, plug in the 2, subtract. So what happens to ln of b as b goes to infinity? This guy, remember the ln graph goes up and up and up, right? So this turns into infinity. So this turns into infinity divided by 2 minus a number, which is infinity. So we know that, so I'll do it right here. So the integral of this ln n over n, I think we went from 2 to infinity. This thing diverges. Thus, by the integral test, we know that this thing, the series of ln over n, does the same, diverges as well. Right? So the series and the integral do the same thing. In this case, they both diverge. Okay. Couple more examples. Not making good use of space, but that's me. So all of this is that first one up there. 5 times n to the negative 2. That's the next one I'm going to be doing right here. So for that one, I'm going to remind you that we can use algebra to simplify things. This would be 5 divided by n squared. And the 5 is a constant. It does not matter. Some people even like write the 5 outside, just like with an integral. You can write constants outside of the integral. It's the same with summations. If it's a constant being multiplied, it will not affect whether it converges or diverges. And the only way it'll affect the sum is it'll be 5 times bigger with the 5 times on the outside. So why am I doing this? Just to emphasize that this is a p-series. P-series is 1 over n to the p. And this, in fact, is 1 over n to the p, where the p-value is 2. If you remember your p-series test, if you have it written down, if you have your formula sheet printed out from Canvas or some other source, for the p-series, it will converge as long as p is larger than 1. Is our p-value larger than 1? Yes, it is. P-value is 2. So for this thing right here, the p-value is 2. So the series, n equals 1 to infinity, of 5 times n to the negative 2, it converges by p-series test, and our p-value is 2. Okay, 2 more problems for this video. And of course, I don't have any space. So I'm going to just rewrite these problems so that a little easier to follow. So this one right here, I'll do it in red, perhaps this one right here, I'll just write down over here. This is the summation or the sum from n equals 1 to n equals infinity of n over e to the n squared. Again, we're going to be able to show that all these numbers are positive. N is a positive number, e is a positive number, n squared is a positive number, e to the n squared is a positive number. These are all positive numbers. These are all positive numbers. They're all positive for n at least as big as 1. And we can also show that this thing gets smaller. We can show that by using a limit. I'll do that this time. This is infinity over infinity. So I can use L'Hopital's rule. L'Hopital's rule doesn't find the limit. It just simplifies the limit. So we still have a limit. But I'll take the derivative of the top. I'll take the derivative of the bottom. Derivative of the bottom is e to the n squared times 2n. And now this tends to 1 over infinity, which is equal to 0. So we have all these positive numbers. They're monotonically decreasing. They have a limit of 0. Therefore, we know that they are, in fact, decreasing from term over term. And so, therefore, we know that the terms decrease. Terms decrease. So we know that they're greater than 0. We know the terms decrease, and therefore we can use the integral test. So let me see if I can just make any sense of this. So we use the integral test. And if you want to practice your integration, this would be a good one to practice on. We're going to do the integral of n over e to the n squared dn from n equals 1 to infinity, but we can't really put infinity up there, so we'll put a b, and we'll do the limit as b goes to infinity. And then we just use our integration techniques to find the antiderivative of this thing, and then take the limit as b goes to infinity. I just put another u sub in there just to practice. It's the most common type of integration technique. So u is equal to n squared works quite nicely. Du dn would be 2n, which means that dn would be du over 2n. And doing my substitution, this becomes a limit as b goes to infinity. I have my n values here. I have n over e to the u, because n squared is equal to u. So instead of e to the n squared, I have e to the u. dn is du over 2n. So we have this nice division of the n's, and the 2 we can write outside of the integral sign because it is a constant being multiplied and therefore does not affect the integral. 1 over 2 integral of, well, we have e to the u on the bottom. I guess I should have done, I should have written it as a negative exponent on the top first, because now I end up with e to the negative u du, which is again another u substitution. I'll let you fill in the details for the u substitution. I think I've done a few of these already, but the integral of e to the negative u is e to the negative u times -1, or divided by -1. So I will leave that to the reader, the watcher, to fill in the details of the antiderivative of e to the negative u. It is negative e to the negative u. And we do got to plug in these values of n, which is 1 to b. So n equals 1 to n equals b. But I'm just going to put it back in terms of the variable n. So I get 1 over 2 times negative, I guess I'll put the negative over here just so it looks cleaner and less confusing. And what is u? U is n squared. So this would be negative. I put the negative in front, and then e to the negative u, which is negative n squared. And then I go between 1 and b, plug in the 1, plug in the b, take the limit, and I determine whether this thing converges or diverges. So I get a -1/2, which doesn't really matter for limits. I get e to the negative n squared, where n is equal to b. So e to the negative b squared minus e to the -1 squared, right? Plug in the b, plug in the 1, and subtract. So what happens as b goes to infinity for this thing right here? This, if you think of it as e to the b squared on the bottom, if b is going to infinity, remember b is going to infinity, so 1 over e to the b squared. B squared is infinity, e to the b squared is infinity. This is 1 over infinity. This will go to 0. We have negative e to the -1 squared, which is just negative e to the -1, which is 1 over e. -1 over e times -1/2 is a converging number. So the integral converges. So the series also converges. The series was n over e to the n squared from 1 to infinity. This also converges. And that's, of course, by the integral test. We're using the integral test. We showed that the integral converged, so therefore we know that the series also converges. All right, my last example is, in fact, the quickest example. This one over here, the very, very last one, says the series of from 2 to infinity of ln n. So this is my last demo problem for this video. And so what's this going to be? Well, I threw this in here just to remind folks that unless the directions specifically, dictate it, you can use any of the tests that you've learned so far. In the previous section, in 11.1, we learned the divergence test, and it is, in my mind, the most important test. It is very easy to check. You just take the limit of the sequence instead of the actual sum. You just look at the terms themselves, ln n. And if that's not equal to 0, you immediately know that the series diverges. That's called the divergence test. So ln n, as you remember, increasing function, right? So therefore, we know that the n goes to infinity to ln n tends to infinity. I'm pretty sure about this, but an infinity is not equal to 0. So by the divergence test, remember, if the limit doesn't equal 0, we know that this series will diverge. So I threw them there just to diverges, just to make sure to remind you that you can use all the tests to help you determine whether things converge or diverge. Okay, so I tried to show you several examples of integral test and p-series test, threw a couple other things in there. This is the end of the video. Hopefully this was helpful. I'm trying to zoom out again so you can see the page, which is usually way too small for anyone to be able to see, and then to zoom in on different parts of it in case people want to take screenshots or things like that. So I do hope you found this video helpful, and that you reach out if you do have any questions or want to work on some of these together. I do have Zoom hours, as you know. I do answer emails as fast as I can, usually the same day. So please do indeed reach out and let me know how I can help. And I do hope you have an enjoyable day.